Okay, let's start. So if any of you are, I know some of you are still waiting to define your project. So again, I'm going to stay in my office for an hour or so after the lecture. So come and talk to me. Also, if your project needs anything to be purchased, make sure to get back to me. Couple of groups have done it. I would like to bundle up the orders, and in some cases I may have the items. So please make sure to kind of do that in the coming days. One final request. I sent a note around. If at all possible, please please message me on Piazza so that things are concentrated in one place. Right now, I'm kind of swamped with sort of emails with very different titles scattered all over, and I get around 300 emails a day from various places. So it's hard to sort of make sure I'm sort of on top of it. So just help me out there. Okay, so again, I'll be there after the lecture for an hour. So last time we looked at how to schedule sharing of a resource. We did it in context of processors when your goal is deadline. And again, just to kind of mention that oftentimes, typically in general purpose computing, our goal is not deadline, but really sharing it with either a rate in mind. So like think of it like your resource as a server, and there are tasks coming in, and you don't want the queue to pile up for long. So on an average, you want to have the things keep moving. So average rate should match of service should match the average rate of arrival. But deadline is different, because when a request comes, it has associated with it a deadline by which it must finish. In a very simple model, it was simply that the requests for a given type of task arrive periodically, and they must finish before the next instance arrived. And then we had relaxed it so that the deadline could be less than that. But there were in this model, there were a lot of simplifications we had done, and I began to address some of them. And one is this whole notion that I may have a situation where things may fail. And the setting out here was, and I had rushed through it towards the very end, so I want to go over it again. So I have a set of tasks out here, and if I were to simply look at the worst case execution time, then you will see that they are not schedulable, even with rate monotonic assignment. That is, I give the highest priority to the most frequent task. But if I look at the average computation time, then it is actually schedulable. So what will happen at runtime is that for any given task, let's say we take task 2, its average computation time is 25, worst case is 30. So it will be some sort of a distribution with the mean of 25. Now what will happen out here is that obviously with some probability, I may be in a situation where the instances that arrive, because for whatever reason, they take more computation time. And usually when we say whatever reason, it could be that the specific data value, let's say this is an image task, and then maybe the complexity of the scene, too many objects in the scene, or just harder to analyze, could be any number of things. So it's possible with some probability that it will miss the deadline. And when it does miss the deadline, then what will happen is that the task which has the highest period, the lowest priority, is the one which is going to miss the deadline. So we want to avoid that. The reason we want to avoid that is because a task which is less frequent may still be more critical, because importance of the task typically has nothing to do with the period of the task. I may have a task which arrives once in a blue moon, but it's super critical. So we want to align this thing. So what we want to do is we want to make sure that when things fail, they fail according to their criticality and not according to the period. Okay, so that was kind of the idea, and the reason this is the variety of other scenarios where it may happen. So in this particular case, I said the peak versus average case computation time. But there are other reasons also, like for example, the processor may be facing a thermal emergency, so it slows down. Or for example, maybe there's too much interrupt overload, a lot of stuff coming in, so a larger fraction of the processor is getting eaten away by kind of the interrupt part, so the rest is remaining for your task. So effectively, the processor capacity goes down. So, so this notion that resources may have variable capacity is pretty commonplace. Another example where a resource may have variable capacity is, let's say, it's a wireless link on which you are pumping packets from different tasks, and it's a very similar setting, and the capacity of a wireless link is a function of interference it faces or the distance between transmitter and receiver. So what again happens there is that at different times the capacity may vary. So what we want to do is, whenever we face with these kind of transient shortage of resource, you want the system to behave more nicely. So now, of course, one possible thing one might think out here is that, okay, hey, why don't we just assign priorities according to the importance? But that we already saw last time that that's not the good way to go, because then you basically are not able to schedule much of the time. So we still want to, in the normal case, we want to assign according to timing requirements, but when there is a shortage happening, shortage of resource relative to demand, then you want the importance to kick in. That's kind of the goal. And the trick, well, one of the approaches is to align the two, so that we transform the task so that if it is a critical task, then it also becomes more frequent, artificially so. And this is a messy thing, but one could do it. And the idea in our system was the following: I have this task which is more critical, but it is less frequent, and therefore normally its priority would be lower, but we want to boost its priority. And the way we do it is we divide it by 2, so that now basically I have sort of 2 half tasks coming at twice the rate. So now the rate becomes 7, and the computation time is, because I have split the task, becomes 3.5. So now second task is this transformed second task is more frequent, and so it will have the higher priority, and I'll achieve my goal. The deadline has to be 6 because the original deadline was 13. So it was 1 less than the period, and therefore you have to make sure that you maintain that even as you are splitting. It's a pretty ugly solution because, as I mentioned last time, trying to divide a given function at the midway point is kind of a pretty hopeless task in most cases. Yeah, you can attempt to do it for simple code, but it's kind of hard to pull off. But cases where one can, and you could take it to extreme. Why stop at 2? You could sort of divvy it up into more pieces and play this game more and more. So basically what happens is that when we divide the tasks this way, we are in effect improving schedulability. And in principle, so our periods were originally 10 and 14. In principle, what I could do is I could divide this thing into 10 tasks of a period 1 each, and I could divide the second one into 14 tasks of period 1 each also. And in that case, I will end up with a very messy looking software, but I would have 2 tasks both with a period of 1. And once you are at that level, then if you go back to your critical instant analysis, the fact whether you can schedule it or not, that condition will basically boil down to whether the fraction of CPU needed by task 1 plus fraction of CPU needed by task 2 is less than 1 or not. So just think of it this way, right? I mean, let's say I give you 2 tasks, and both have a period 1, and one takes CPU time 0.2, the other takes CPU time 0.5. Then in the critical instant, they'll arrive at the same time. Whichever I give the higher priority to, it will run, and the next one will run. And as long as the computation times are less than 1, I'm good to go. So in the extreme case, where I split it down so that all the tasks have the same period, then my schedulability requirement basically boils down to that processor utilization is less than 100%, which is a great situation to be in, because if processor utilization is more than 100%, I obviously cannot schedule. And if my periods are all equal, then it will certainly be, if utilization is less than 100%, that in other words, the fraction of CPU needed by the task is less than the capacity of the resource, then I'm good to go. The more general result is that if I give you a set of tasks whose periods have a harmonic relationship, that is, they are multiple, the periods are multiples of each other. So let's say one task has a period of 2, the next one has a period of 4, another one has a period of 8 or 6 or whatever, something like that. If there's a harmonic relationship, again the same requirements holds true, that you can show that my the system would be schedulable if the capacity is enough and all the deadlines will be met. So so what this whole period transformation, in essence, I can keep playing this game and until either my periods are in a harmonic relationship or are they equivalent. So, for example, if I transform this task to this kind of situation where first task is split so that its period is now 5 and the other one is 15, they are in a harmonic relationship, and in this particular case, it's enough to show that their the processor capacity is enough. So so this way of transforming the task is pretty much your only solution available to align priorities with importance. Second issue that want to touch upon. So what happens if there are tasks which are irregularly arriving? So thus far our model was they're always arriving in a periodic manner, but what if I have some tasks which arrive in a non-periodic manner? So what is typically done is that in this particular case, we basically say, okay, I would still need to know how close apart 2 instances of a task may arrive. So let's say there's a task which happens because of some asynchronous phenomenon. Then if I know nothing about it, then of course I have a problem because 2 instances may arrive arbitrarily closely. So what we are basically, the assumption typically which is made is that if that aperiodic task has a deadline, then I would need to know what is the minimum separation between this aperiodic task. And then we essentially think of it as a periodic task and go ahead and schedule. If on the other hand, you have a more relaxed latency requirement there, then what is typically done is the following, that we'll assume or we'll implement it as if in my system I have a very high priority process, the highest priority process. And it's kind of it's a server process. So every so often it arrives at a certain period, and my CPU switches to that, and this server process runs. And this server's job is to take care of those asynchronous tasks. So the asynchronous tasks, when they arrive, they go into a queue, and then the server, which has the highest priority, is going to pick them up and process it, but only for a certain period of time. So in effect, what we have done out here is we have taken a certain capacity of the processor and set it apart for those delay tolerant tasks. And this is like a server which is processing a queue, and as long as the average, the fraction of the CPU or fraction of the resource I have set aside is enough to meet the overall load of the asynchronous task, this will work. So what may happen though is that the delay can be a lot, but you can analyze such a system using queuing theory type methods, which if you have done any communication course, you would have encountered them, right? So you can think of, I essentially have a server for a queue, which corresponds to whatever fraction. So let's say if it was a CPU, 10% set aside. So you can think of it as if I have a CPU with 1/10 the rate. or if it's a communication link, same way. And then your aperiodic, your asynchronous tasks, they're arriving, they're sitting in a queue, and you are processing it, and you can bring all the mathematical machinery for queuing into this thing. And meanwhile, what is happening is that certain part of the CPU has disappeared. So when you are doing the delay analysis for the real-time tasks, for the ones which have a type latency, and okay, you have to account for this additional thing because some part of the CPU can disappear. So you can think of it as the highest priority task is eating away this much time. So it enters into that interference number, that interference term that we had talked about last time. So handling asynchronous stuff, sporadic tasks, is done a simple way of doing it is like this. Question?
Why can't we make this the lowest priority then? Because anyways we are taking care, like they are having good latency.
Because you may starve them out also. So, but you're right. I mean, you could play with these things, and there are alternative configurations also. This is not the only one. So you can think about what the implications are. One of the things which is done is, let me go back out here. In this particular case, what happens is, let's say the server task started, and let's say at that time the queue is empty. Then what will happen is we will relinquish the CPU, and the real-time tasks will start running. The periodic tasks will start running. But the question, one of the things is, what do I do with this time? Like, because I did not make use of it, because when the server started, there was no one in the queue. So one variant, just along the lines of like your question, is that when the server task came at this instant, the third clock tick, there was nothing in the queue. So we delay it until there is something in the queue. So in this particular case, we say we don't lose the time, we still retain it. Or likewise, in the first frame, something similar happens. So this model is called deferred server. So now let's talk about your example. What would happen if I were to make the server for the aperiodic tasks to be the least priority one? What do you think would happen in that case? What are the implications? And let's say let's say we make sure that in the worst case we are still meeting the thing. So I guess the question, what it will really boil down to is that this particular task may now get interrupted in the middle by everything. So how do we make sure that, so I guess the reason they end up doing it this way is that the delay analysis is a lot easier for the sporadic tasks, because otherwise what will happen is that the delay analysis for the sporadic task becomes horrendous. So that's so in this model you can still make some statements about the delay guarantees for the sporadic task, whereas if you were to make this guy the lowest priority, then you would have a much bigger problem. Okay. Another issue which comes up is the uncertainty in execution time. So we saw that in the very first slide in today's lecture also, which is we had this average time versus worst case execution time, although there we were simply worried about missing the deadline. So thus far our model had been that we were scheduling things with the case in mind that even in the worst case we are meeting the deadline. Now, as you might imagine, if you are in a setting where worst case is much greater than the mean execution time, then this is pretty conservative. You are basically budgeting for a unnecessary powerful CPU, because it could be that the execution time has a long tail. So just to cater to a tiny fraction of instances which take a long time, you are basically budgeting for a very powerful resource, too much resource. So there are a variety of ways one can deal with this thing. One way is that fine, we are still going to budget for the worst case execution time, and what will happen is if the task takes less time, then I have some spare CPU time, right? So one thing I can do is during that spare CPU time, I can use it for other tasks, kind of non-real time stuff, other things. Can you think of something else that you can do if the task finishes early? Yeah, yes, like how can I beneficially use that information?
Maybe decrease the voice case, like time allotted to it dynamically.
No, so the task started running and it just finished early.
Yes.
I thought it will take 10 seconds, but it took 8 seconds.
So that 10 seconds that you're thinking will be reduced dynamically.
No, but remember how this operating systems work, right? They hand over a task, and when the task finish or right, I mean, so it's not like I can reduce anything. I'm just all I'm doing, all the OS is doing is giving the resource to the highest priority ready task. It's just that the OS assumed that the task will take its worst case time, but it actually finished earlier. So in normal course, what will happen is the next lower priority task will run and all, right? But obviously with this thing, what we'll end up with is that there will be some more idle time in the CPU. And naturally, in that case, you can shut down the CPU. That's one option. You can save power. Another possibility is the following. In some cases, when the task arrives, right at that point, maybe you can get to know that this instance is going to take less time. Like you can examine the arguments of the task and say, this one is a good case for me. It will take only less time, 5 seconds. And another one, this is a bad one. It's going to take me 10 seconds. So if by examining the task, you could quickly estimate what time it might take, then you can lower the frequency of the CPU so as to eat up all that time. So there are a variety of beneficial ways you could use that. You can use that information. You can use it for other stuff, like donate the CPU capacity for other traffic. It's kind of maybe rent out that capacity for some purpose. I suspect if you have used Amazon Elastic Computing, they have this notion of spot pricing where you can bid and stuff like that and all. So these kind of systems can certainly benefit from spare capacity, because if there is unanticipated spare capacity, you can kind of rent it out. You can shut the CPU, you can slow down the CPU, all those kind of things can be done. But there's another thing you could do, which is the following. Instead of budgeting for the worst case, I'm going to be an optimist, and I'm going to design the system not for the worst case execution time, but let's say for the mean execution time, or maybe mean plus a couple of sigmas. Now, what will happen is, since I am not factoring in the worst case, so with some probability, an instance may arrive which would take more time than what I had budgeted for. So let's say I budgeted for the mean, but I get some instance which, well, now I'll get half the instances, not half, this is a mean, but I'll get some instances which will be above the mean, and of course they are going to miss the deadline. So the trick we play now is the following. We create multiple versions of my algorithm. So let's say we are doing some sensor processing, let's say neural network, okay? And the sensor samples arrive, and I have to process it. And I budgeted some time for it, but it turns out, hey, it's going to take more. So what I do is I make a precise version, but then I also create an alternative version. And this alternative version is designed to take a shorter amount of computation time. It's presumably, therefore, if it is going to take shorter amount of computation time, it must be bad in some other regard. Like maybe it needs more memory, or maybe it gives an inferior result. Very typically, what might happen out here is that maybe it will do some quick and dirty result. Maybe it may say, this instance of neural network is going to take too long. I'm going to just use a linear regressor, a simpler model, and just get it. Or maybe I'm going to use a simpler, smaller neural network which can compute faster. There could be any number of things, and you can imagine the same type of policy in other settings also. So let's see an example of that. So this is some task, and with a period of 15, and I have two instances, two implementations of this task. Same algorithm that do the same thing, same input, same output, notionally, but one of them, one implementation, has an average runtime of 7 and can take as much as 20 time units. And the other one has an average runtime of 4 and can take only, in the worst case, of 5. So now let's imagine at time 0, I started running and I have a deadline of 15. Remember, normally we switch back out here, deadline equal to period, so I want to finish in time 15. Now if I only implemented the primary one, then on average I will certainly meet the deadline. This only takes 7. But with some probability it might exceed 15 and therefore it will miss the deadline. The alternative one gives me an inferior result, and even in the worst case it finishes in time. So one option could have been that I'll just run the alternative and then I'm happy all the time. But then the quality is uniformly bad all the time. So what I also want to do is I want to run the high quality task as much as possible. So the trick now is that we'll start running the high quality task, and then there will be some point when it's a point of no return. And that point of no return would be t equal to 10. Because at t equal to 10, 10 units have already transpired. We know that the worst case execution time is 20. And so we may still go for another 10 time units. And meanwhile, my alternative takes at least 5 units. So I have to make sure that now I switch over to alternative. So I need to switch over to alternative, deadline minus worst case of the alternative. So that would be 10. So at t equal to 10, if the primary, my main implementation still hasn't finished, I switch over to the alternative, discard whatever computation we did out here, and kind of go with the alternative one. So we'll still have a timely result, but a less accurate result. And fortunately, a lot of algorithms, signal processing algorithms and all, they all are amenable to this kind of trickery, because we can always implement them with an inferior version of it, a noisier version, a lower precision version. One could do these kind of things. So that's one approach, right? That I create a primary version and an alternative version. Another approach is to create algorithms which I can stop anytime. So these algorithms are, you can think of them as, if I give them more time, they give me a higher quality result. If I stop them early, they will give me a poorer quality result. So usually these are iterative algorithms, and I can stop them after a certain number of iterations, and they'll just give me the best result they have thus far. A lot of search algorithms are like that. They keep track of the best seen thus far, and if you stop them early, they'll just dump that as an output. Any sort of iterative, a lot of iterative numerical algorithms are like that. Algorithms which are implemented in a bit serial manner, they start computing the most significant bit and then the next most significant bit, and so on and so forth. They have the same characteristic also. If you're computing, so the trick is you compute from the MSP side so that you can stop at any time, and then your loss is on the lower precision bit size. Tree search, a lot of stuff falls into this is amenable to this kind of trickery. So again, kind of the takeaway message out here is that we can either have this alternative algorithm and we switch to that when we reach the point of no return, and the other approach is that we create these algorithms which could be stopped at any point in time. And this whole area actually has regained, this second category has regained a lot of attention in recent years, although for a different reason. So nowadays it is often referred to as approximate computing. And the reason it has gained a lot of attention in recent times is for a phenomenon which is referred to as variability in computer chips. So what variability refers to is the fact that the intrinsic speed of the hardware of, let's say, a processor or a custom chip that you have depends upon a couple of things. One thing it depends upon is the environmental conditions. Temperature affects the speed, for example. Okay, well, actually, kind of three things really. So temperature affects the speed. Another thing it depends upon is the age. Normally, we don't think of circuits as something which age, like biological things and all, but circuits age. As they are used more and more over time, there is a degradation that sets in. They kind of slow down. Okay, so there are kind of well-characterized aging curves and all. And the third one is the precise dimensions of the circuit, transistors in the circuit. So these circuits, as you know, are made by literally kind of etching things out on a piece of silicon and all. But when you look at, so they're made like on a single big wafer of silicon, many copies of the same chips are made. And if you examine two copies at different parts of the wafer, or a chip across different wafers, like as we are making many of them, you'll see that there are tiny variations, because literally what you're doing is you are kind of drawing things out on silicon, and we are drawing dimensions which are at sub-nanometer now. So even a single atom this way or other has a high percentage implication on the dimensions of the transistor, and consequently on the speed of that gate. So you may design it thinking, okay, this is a dimension of the transistor, but there's significant variation in it, and therefore when I take two identical circuits, they just happen to be put on different parts of the wafer or on different wafers they were produced at different times. There are slight differences between them, and those differences can actually be quite significant. So the issue that is being dealt with is in this approximate computing now is that you may design something for a chip, except that you may be lucky and the particular chip you get is a fast one, or you may be unlucky and a particular chip you got is a slow one. If any of you are into gaming, as you know, gamers spend a lot of money and all to kind of identify fast CPUs, they overclock them, stuff like that, to just squeeze more out of them. So that points to the fact that they're again exploiting this variation. So when Intel sells you a processor, or a company sells you a processor, and they say, okay, it's a 100 megahertz processor, it's not as if all the chips they are making are 100 megahertz period, right? There is a spread in the speeds of the chips that are produced, and they have set that 100 megahertz to be a threshold where they have good statistical confidence that most chips are going to meet that 100 megahertz rate, but there would be some chips which may be, there'll be a lot of chips which may be faster, and hopefully only a small number which will fail, so that we still maintain happy customers, there's no failure. So the reason approximate computing kind of helps us out here is that there is a lot of emphasis in recent times on creating software which can gracefully adapt to the change in speed of the underlying hardware. Those of you who use GPUs, if you have, you would have noticed that as well, because GPUs consume a lot of power, so they are particularly amenable to temperature-related environmental conditions. So if you run that machine in a room which is not properly air-conditioned and all, your supposedly fast NVIDIA 2080 Ti might actually be crawling at the rate of much lower cost GPU. So we face this phenomenon quite a bit, and the trick now is to create algorithms which can just gracefully adapt to this thing. So again, a lot of algorithms fall into that category. Not everything. I mean, I don't want, I don't know, like my compiler to do an approximate compilation. I don't know what it, well, even then, can you imagine something that the compiler, what would an approximate computing compiler do? It can't output an incorrect result. So what can it do differently?
CISC to RISC.
Huh?
CISC instruction set to RISC instruction set.
No, it's the same process for the same processor, so you can't do anything different. You still have to produce correct code which does correct computation for whatever program you have written. So can you think of something that the compiler can do less of while compiling?
Less optimizations?
Yeah, optimizations, exactly. Because compilers invest a lot of time on optimizing your instruction set for speed of the produced code and all. So what this compiler can say is, right now I'm running and I better finish in time because the CPU is crawling. So maybe it will just gracefully just not do some compute intensive memory optimization or code optimization. So actually, when you start out thinking, there might not be anything I can do out here, but maybe there still is that could be gracefully done to kind of slow things down. If you're playing a video, you can lower the resolution or lower the frame rate. Search I already talked about. You can kind of if it's Google, which is searching for, like you type a query into Google, it goes to Google servers, they can easily do a approximate kind of thing, right? They'll just search less. You wouldn't even notice, right? Because your first few pages are probably going to remain the same. It's just the tail of those queries change. Signal processing I talked about. So this approximate computing has become a very well accepted paradigm now. So back to our, like, how do we think about these in a scheduling kind of approach? So one thing that is often done is now that we move away from saying there is a hard deadline, because hard deadline meant that if I failed even by a teeny bit, then I basically have failed, to one where there is some sort of a softer notion of failure. So a very common model which gets used is often referred to as increased reward for increased service. But kind of the basic idea is that you can think of your task as having a mandatory component which you must finish, must get, like this much time the task must have. And then there is an optional time. And we want to give more optional time if possible, because that will make the task utility higher. But that's optional, but mandatory is enough. So in the classical model, if you may, that we had previously done, optional part was zero. Everything was mandatory. Either you meet the, so your goal was to meet the mandatory, and if you failed to, then you failed. To now one where we'll say, okay, you must meet the mandatory, and you should provide as much of the optional as possible. Okay. And usually in this kind of model, you would now have some sort of notion of utility. That is, the more I give a task, the optional component to the task, the more return I'm getting in some manner. So a very simple model could be something like the following. We're thinking about the following, that if the allocation I give to a task, let's say the CPU time or the bandwidth or amount of memory or whatever, if it is less than the mandatory component, then the reward that task is getting, the utility that task is getting, is zero. If it is more than a certain threshold, then there is a saturation. I don't get any additional benefit. That's also very common, right? For example, if it is a video playing thing, after certain resolution or after certain frame rate, we cannot even observe anything. So it's kind of pointless, right? It saturates. And in the middle, it would be some sort of monotonically rising function or monotonically non-decreasing function of the thing. So as we move, as we head from just giving m to giving some O plus m, I get kind of, the task gets more utility. So this concept is very common. It has been particularly common in networking. Thing is often referred to as quality of service, QoS. But kind of the notion is that the more X I'm giving, a better service I'm getting out of it, with some minimum service requirement of M and maximum service beyond which I don't get any additional gain. So you are wasting a resource at that point. And in the middle, how it rises is really an application dependent function, right? You can't say, other than making a statement like more rewards will not hurt, you can't really make any other statement depending upon, let's say if it was how does the satisfaction of a human listener changes with increasing sample rate, or how does the satisfaction of a quality of a movie, how does it change with the increased frame rate of a video? All these kind of things are very inherently very subjective, and you can't answer them in an application independent manner other than to kind of frame it like this. So our scheduling problem now boils down to is I'll have a set of tasks, and to each task I have to give certain resource, certain amount of the resource, and my goal would be to maximize R, maximize the total utility of the overall system. So I'll basically have a bunch of tasks, I'm going to schedule them, and each task, based upon how much of the optional time they are able to get, optional resource they will get, they will have overall satisfaction, reward, and your goal would be to maximize the reward. So this is essentially an optimization problem. That is, you are trying to do an allocation of resources in order to maximize an objective, in this particular case, the overall utility. By the way, this could be done with deadlines, but it could also be done when there are no deadlines and you are just trying to parcel a resource. Okay, let's say you have a bunch of users and they all come up with saying, one says, I need so much rate. Another one says, I need so much rate. Okay, and if you were to try to give all of them O plus N, then you will not be able to accommodate them. So you have to penalize some. So intuitively, let's say I have a bunch of tasks, and if I were to give all those tasks, both optional and mandatory, I cannot fit them in. And let's say for now I'm only worried about that there's no deadline constraint, so essentially I'm only worried about the processor utilization. Okay, one task needs O plus M for one task is, let's say, 50%, and for another task is 75%. So if I put both of them together, they need 125% of the CPU, which I don't have. So I have to reduce them. Now let's say the mandatory component of both of them is less. Let's say it is 30 and 30. So if I only do the mandatory, I'll leave the CPU idle for 40% of the time. So now I have to think about the spare capacity above mandatory. How do I allocate it? So intuitively, who would you give the CPU time to? Exactly, right? The rate, whosoever makes more efficient use of the CPU, derivative of reward over the given resource should be high. So you're going to look at the marginal, like how efficient a task is in deriving reward from one additional unit of reward, one additional unit of the resource that you are giving. So you can think of heuristic approaches to kind of do it. Another approach is nowadays, but particularly because task sets are often very small and all, and if you're trying to do this stuff statically, then there are perfectly great optimization, nonlinear optimizers out there in MATLAB and all sort of packages which are floating around. So you can formulate this thing as an optimization problem, feed it into one of those optimizers, and it will tell you what the X's are. So there are a variety of ways you can kind of approach it. Obviously, there are no closed form analytic solutions to these in the general case. So these are the kind of things that you would have to resort to. It's a nonlinear optimization problem. The trick, though, is that the challenge, though, is that if this is being done by an OS at runtime, a set of tasks come in, and now I have to decide what do I do, how do I run it, then of course it's a lot more challenging because a lot of these optimization stuff and all take a long time. So then some quick and dirty heuristics would be what you would use. Okay, let's see. Then the next thing that I want to go after is, and this is a biggie, so tasks which are not independent. So thus far we had assumed that the tasks are independent. They don't interact, they never share anything, they don't message each other. So it's never the case that a task has to wait for another task or anything. Okay, the only thing is a request arrives and a task runs. There is no interaction between them. But for almost any useful system, tasks do have to interact because they share kind of data structures to interact with each other. They share hardware resources, like for example, maybe two tasks can both be sending a message over the network. Maybe they'll share sensors, maybe they'll share actuators. There are a lot of things that they generally might be sharing. Moreover, a lot of these things are non-preemptible. What I mean by that is, once a task starts using a resource, I cannot stop it in the middle. So think about like when you send a packet over a network, right? Let's say there's a task which is sending out bits over an I/O interface. If you were to stop it in the middle, then you have thrown away all the work you have already done, because you can't just stop a packet in the middle and resume it later on. So there are certain things in our systems just have to be done atomically. Okay, so which basically means once we start doing it, no preemption. Okay, we basically are going to lock out the operating system somehow or other for that purpose. Unfortunately, all these things make the ability to meet deadlines, or at least analyze the deadlines, a lot trickier, because what might now happen is that there could be long periods of time where I am a high priority task, I'm ready to run, but I cannot proceed because I need a resource which some low priority task has grabbed, and now I have to wait for it. Previously, we never had that situation. Previously, the only thing which could preempt me was tasks which are more high priority than my task. But now we can have these situations where a task which is lower priority can basically stall me. And somehow we have to account for that in our analysis. And moreover, somehow we need to make sure that bad things won't happen as an interaction of this, as a result of this. So this phenomenon is called priority inversion, because in a sense what is happening is, because of this resource sharing, a high priority task in effect is kind of behaving like a low priority task. So this is an example. Let's say I have a couple of tasks, call them tau 1 and tau 3. They share a resource, let's say a radio, a sensor, something. Let's say task 1 has higher priority and task 3 has the lowest priority, and there is another task 2 which has an intermediate priority. So task 1 highest, task 2 middle, task 3 the lowest. Now take the scenario. Task 3, that lowest priority one, locks the resource. What we mean by that is that there is a semaphore call it makes, and then locks the semaphore which is protecting that shared resource. Then after task 3 enters this critical section, that is, it starts making use of the resource, task 3 becomes ready. An external interrupt arrived and it activates, task 1 becomes ready. So task 1 is now active, ready to run, and task 1 will start running, and then at some point it needs the shared resource because it also uses the resource. And what it will do is it will try to lock the semaphore. Now if you recall, the semaphore had two functions, wait and release. So what this task is doing is it's going to execute the wait on that semaphore, except that semaphore is already locked. So task 1 cannot enter it, so it will be put onto the wait state. It will have to wait until the resource is free. But let's say what happens now is, meanwhile, task 2 became ready. Now task 2 is higher priority than 3, so task 2 is ready to run, and therefore it will get the CPU, and meanwhile task 3 cannot run because task 2 is able to run, and task 1 is waiting for the resource which task 3 has. So we have this kind of waiting, we have entered into this adverse situation where task 1, even though it's higher priority than 2, but 2 is running. So effectively task 1 is acting as if it is lower priority than 2, even though ideally we would like it to happen. And I had discussed this example the last lecture as well, something very similar. Intuitively what we would like to do is somehow make sure that task 3 temporarily inherits the priority of task 1, right? It begins to act like a high priority task because it is responsible for waiting, for causing task 1 to wait. So, so what we would prefer is that task 1 should not be blocked, should not have to wait for any more time than what task 3 needs to finish its job. So what we would like to do is task 3 should run, finish using the critical resource so that task 1 can run. So that's what we want. But in reality, in the way sort of thus far the mechanisms that we have is task 3 can be preempted many, many times by task 2. In fact, task 3 may have to wait a long time before it finishes. So we want to avoid this situation. We would like to make sure that task 3 doesn't take any more time than that piece of code which was using the shared resource needed. But in the current setting, it may take an arbitrarily long time depending upon how many times task 2 arrives during this process. So all of this might sound like a contrived problem, but like as I had referred to last time, actually the way this thing came to consciousness awareness in the research community was when there was a pretty high profile failure. So this is 97 Mars Pathfinder, which was this little robot rover kind of thing, which was going around Mars, collecting sensor data, processing it and stuff like that. And after landing, this was the one where the ship had fallen down with kind of, they had a lot of protection and all, bounced around and all, and eventually kind of this robot had come out and all. And there were all these media reports there where that it was repeatedly rebooting in effect, okay? And so after this thing had started collecting sensor data, there were these glitches, so to say, where the hardware would reset and again and again and again. So what happened deep down was the following. It was exactly this priority inversion type of a situation. So there was a set of tasks, and kind of the precise details don't matter as much, but what was happening in effect was the following, that precisely this tau 1, tau 2, tau 3, the 3 task kind of a situation where there was a high priority task, their software called BC dist. It was blocked by a low priority task which had grabbed the resource and which was getting preempted by a medium priority task. And moreover, what happened in this particular case was that how much work that these lower priority tasks were doing, it turned out that there was more interesting sensor data being captured, so the workload was higher than what they had assumed it would be. So it was coming in much more frequently. And meanwhile, so consequence of all of this was that this high priority task, BC dist, was seeing deadline misses. Moreover, there was an even higher priority task which was in the system, even higher priority than this, and whose job was to do some scheduling work for the next cycle in the processor. And in particular, what it would do is it will check whether this BC dist finished in time or not, and if it didn't finish in time, it would reset the system. So this resetting the system when things appear to have hung or something bad is going on is a very common strategy in embedded systems. It is often referred to as a watchdog timer of sort, but the idea is that you keep an eye on the state of the software, and if something weird seems to be happening, then you kind of bring it back to a known state, kind of just restart the system. In many modern processors, this is provided at a hardware level. It is essentially interrupt which cannot be disabled. And kind of the idea is that the software is supposed to go and reset that timer. So imagine like there is a bomb ticking, and you're only once you have started the bomb, it will detonate unless you stop and reset it. Okay, so the idea is that one of these tasks, the high priority task, was supposed to observe, and if the deadline was missed, then it would basically fail to the watchdog timer will go off. In this case, the implementation was done somewhat differently, but the concept is the same. So in processors which do have the watchdog timer, typically what is done is that the application is supposed to go and reset this watchdog timer, and if it fails to do it, that means it failed to meet its deadline, and therefore the whole system will restart from scratch. Okay, so in this particular case, that's basically what began to happen. The system would reset, and like I said, the media reports basically were that there was some software glitch, but the glitch in this particular case was precisely kind of this combination of priority inversion. So what they obviously they missed it, right, because they shipped whatever the system onto Mars, but they did have a replica on the Earth. And when you are a NASA and your whatever computer is far away, then you take all sort of other precautionary measures around it. And in particular, they had a trace logging facility so that they could download what was happening and all and attempt to replicate. Okay. One thing was that they had noticed these glitches, sort of say, on rare occasions on Earth prior to the mission going out, but apparently, I guess it's the usual software hardware kind of tension. So software, some hardware glitch happens rarely. Let's worry about it. We have the reset mechanism anyway to deal with it. So they kind of shipped it. Except because of this, what they didn't realize is that the cause of those glitches was not some rare hardware issue, but rather a systematic software bug. And it just so happens that during the actual mission, the lower priority task had more workload, and therefore these resets started happening more frequently. How did they fix it? So it turns out that these semaphores that we have, which you can take, lock the semaphore and unlock the semaphore, they have in the operating systems they were using VxWorks, which is a commercial operating system. And one of the things that VxWorks was that from the shell, our command line, the terminal, you could globally change the behavior of all the semaphores in the system, so that so that they start making so that they enable what is called as priority inheritance. In effect, what it means is precisely intuitively what we want, which is that if a task has locked a semaphore, then its priority will be the priority of whatever task it is blocking. Okay. So what they did from Earth was they basically patched the code, essentially sent a diff of the code so as to make all the semaphores global. Now again, when you are sending code that far away, you can't really send a huge binary and all, right? So it's only very localized changes, and fortunately VxWorks made that easy, and they applied that patch and it got fixed after some weeks into the mission. The reason it was not caught was, as I mentioned, because it was observed, it was attributed to rare hardware failures, whereas in reality, what was happening was a software bug, and it was more frequent because of an increased load at runtime. So that was what happened. Yeah, question.
Do you know, is that option to enable priority inheritance common in a lot of operating systems, or do they kind of get lucky that
VxWorks is pretty unique in that regard? At least, like if you were to be using Linux today, there is no such provision. Okay, but then also remember, at that time the consciousness of this thing just wasn't there. Nowadays, at least one would hope that people who are designing these things are aware of these issues, and perhaps even the default setting of the semaphores would be like that. We are talking about a time when the papers discussing priority inheritance mechanisms and all had not even come out. So this is kind of, and remember, a mission going out in '97 means that software was done some years prior to that. Right? These kind of issues have been suspected in other contexts also, like these kind of things where some poorly understood aspect of software being accused. Okay, I mean, some years ago there was this whole episode around Toyota's braking system that was often alluded to being because of some failure. Nowadays, what has begun to happen is that there is this whole area called formal verification, which has come in, which literally takes your system software and it can analyze and find out these mistakes. So you could basically say, test my software so that it will never enter the state, and essentially kind of like proving a theorem, it will try to prove that your software is correct. So so certainly the emphasis has switched away from simply testing to proving. Why do you think testing is not enough? Like software, I can test it a lot. These guys did it. Why is testing?
Because you miss out few states.
Yeah, so the problem with testing is that you can never test exhaustively, right? Because your input space is huge. So you're at best going to do some random thing. I mean, and even that we don't even you kind of leave it to the humans to kind of figure out what the corner cases might be and all, and you miss a lot of stuff. In these kind of things, these kind of timing problems and all, things are even harder because you're trying to achieve certain timing relationships for the bug to be triggered, and this is something you can't even do by just changing the values of the input. You have to have precise control over the timing. So pretty hard to debug, and it's best left to these modern tools which are emerging. The flip side though is that right now those tools are very primitive, in the sense the kind of things they can test for are very limited. But we are now in a stage where we have entire operating systems. There's some recent work I saw out of Microsoft and CMU where they have even sort of begin to formally verify some of the security protocols and all, like really prove that there is no security bug. So things are a lot different now than what they used to be, but still long ways to go in this thing, and it's an active area of research. There are huge research programs just focused on create tools which will help verify the correctness of the software. Okay, loosely speaking. So this was along there. So yeah, let's see. Any point I yeah, okay. So essence out here is that just testing type approaches really are quite limited, and you need to be able to. Ideally, you would want to be able to analytically formally show that your software is correct. And this kind of brings to this point that these tricky aspects of systems, it's important to follow systematic design strategies, not simply, it's missing deadlines, let me just speed up the processor, or it's missing deadlines, let me just, okay, I mean, and oh, wow, now it's not missing the deadlines, but then when you're testing, you're kind of testing like a tiny fraction of the whole input space. So not a whole lot of assurance there. And I think in this regard, our profession, software and electronics, is kind of a bit different than civil engineers and mechanical engineers and all. I mean, they have much more systematic way of like, okay, I'm designing a bridge and we're kind of taking into account overload conditions, stuff like that and all. They kind of approach it much more analytically, but then in a way the systems they create are also logically a lot simpler. There are a lot more moving parts in a software in your car than kind of even the most complicated of the bridges. So I think our ability to analytically approach these things is still not there. And what I'm describing is, I mean, this is late 1990s, so we are already looking at 20-year-old stuff. And there are lots and lots of other issues which currently exist. Okay, so what happened then is that solutions to these were around that time emerging. Like I said, this in the 90s, this accident happened, but around the same time, the techniques had also started coming out. Much of the work happened at CMU around this thing. So I'm going to walk you through some simple example to kind of motivate how these techniques work. So main thing is that there is the modern methods rely on something called priority inheritance, which I kind of referred to earlier as well. And I'll show you by some examples that how they work. So let's imagine I have a system with 4 processes, 4 tasks. And just to keep things simple, we are not going to worry about periodicity or anything like that. I have just 4 tasks. Their priority, I'm looking at like an instance of each one of these tasks. Their priorities are 4, 3, 2, 1, exactly in that order. And they arrive, the instances of these tasks arrive at times 4, 2, 2, and 0. So at t equal to 0, a copy of L1 arrive, or whatever, L1 arrive. Then at t equal to 2, L2 and L3 arrive. And at t equal to 4, L4 arrive. And the computation these things are doing is like the following. There are 2 resources, Q and V. There's 2 shared resources. So Q is used by L4 and Q is used by L1. So, and it's denoted by the fact that it's using Q for 1 time unit, whereas this guy needs Q for 4 time units. There's also a resource V, which L4 uses. So what this is saying is L4 executes, uses Q, uses V, executes. Okay. So L3 does normal execution, uses V for 2 clock cycles, or two time units, and then execute for 1 time unit. L2 doesn't use any of the shared resource, and L1 executes normally for 1 time unit, has 4 time units of Q, and then releases Q, and then just executes. So this is what's going on, and if we were to see that if we were to not do anything specific, just let the system run based on priority-based scheduling, the following is what will happen. L1 arrives, it does 1 normal time unit of execution, then grabs Q. At t equal to 2, L3 and L2 arrive. L3 does, and their periods, their priorities were L3 was higher, so L3 executes for 1 time unit, and then L3 needs the V. So the difference between Q and V is based upon the direction of this diagonal line. So the one L3 locks V. So now what has happened is Q is locked and V is locked. Then by this time is t equal to 4, L4 arrives. L4 starts executing. It executes for 2 time units. Meanwhile, 3, 2, and 1 are waiting. So this priority-based ordering. Now L4 needs Q, except Q is locked by L1. So L4 will go into the wait state. So L4 goes to the wait state. So next highest priority task is L3. L3 is ready to run. So it will run 1 more unit of the shared resource, and then it will run normal execution time. It releases, it gives up the CPU, but Q is still locked, so L4 cannot run. So now L2 starts running. L2 only ran for 2 time units of normal execution, so it does it. It gives up the CPU. Only then L3 runs. L3 does 3 more time units of Q. At this point, it releases Q, and as soon as, so at 14 or 13, something like that, at this point it releases Q, and as soon as it releases Q, L4 will get the CPU, it will finish its job, and then L3 will finish it. So what's happening out here is, as you can see, L4 is a high priority task. If there was no sharing, L4, when it arrived at t equal to 4, would have just raced ahead and finished. But because of all this interaction, it has a long period of time when it is unable to run. And ideally, we would like to keep that time to the bare minimum, right? What we would like is that when L4 arrived at this time, then at time 6, it should just be able to race ahead. Now, there is also a slight challenge out here that it needs 2 resources, right? It needs Q and it needs V. In our case, right now, the job is simple. It needs Q first and V later. So what we would like to do is, it should not have to wait more than 1 time unit for L3 and 3 time units for L1. So it should not have to wait for more than 4 time units. So we would like it to resume at 10, okay, in the worst case. So let's see how we go around achieving that. So, so now let's look at what the solution. Just give me a sec. Yeah, okay. The solution turns out to be for this thing. So there's the algorithms which have eventually emerged as the solution to this problem are referred to as priority ceiling algorithms. And intuitively, the idea behind them is that we assign priorities to resources also, not simply to the tasks. So thus far our model was tasks have priorities, resources are just resources. So we'll see how that plays out. So now in a simpler setting, a simpler example to see this thing. So I have two tasks, tasks 1 and 2, and they have two resources, S1 and S2. And I want to highlight kind of a challenge, another challenge that these systems face. So I have task 1, and task 1, what it does is it locks S1, locks S2, uses the two resources, and then unlocks S2, unlocks S1. So it is nesting the resource usage. Whereas task 2 does things in the reverse way. Locks S2, locks S1, unlocks S1, unlocks S2. Now you have a even more obnoxious potential for an obnoxious problem, namely a deadlock. So what can happen, for example, is task 2 may lock S2, then task 1 comes, locks S1, and now needs S2, but S2 is locked, so it gives up. Task 2 starts running, it needs to lock S1, but S1 is already locked. So now both are waiting. This is a classic example of a deadlock problem. Task 2 needs S1 and task 1 needs S2 to proceed, and there is no way of kind of going back. So what should we have done out here?
Task can tell which resources it wants.
Say it again?
Task can tell which resources.
Right. So at some level, we need to at least achieve that effect. Tasks, unfortunately, tasks can tell what resources they want, but they cannot tell when in future they will need, because that may depend upon precise computation. But your intuition is absolutely right, that what we would like to do is, if task 2 has locked S2, then we want to make sure that task 1 is not able to lock S1. Right? We would like to have that effect. And for that to happen, somehow we should know that S2 and S1 are used by these two tasks, so that the operating system can say, hey, you're trying to lock S1, but you know task 2 needs it too, so let's not proceed because there is a potential of a deadlock. So how we achieve this effect is the following, is that we begin to assign priorities, or what are called as priority ceilings, to resources also. So we basically you would see that resources S1 and S2 will now also have priorities, and they would be the priorities of the highest priority task which can use those resources. So that's how the OS will keep track of it. So what will happen now is the following. Task 2 arrives first, it starts running, and it locks S2. Then task 1 arrives at t equals at some time, it starts running, and then it attempts to lock S1. Except we don't want it to proceed. And the reason we don't want it to proceed is precisely because there is a risk of deadlock which is happening. So what happens in this particular case is that we basically try to, when it attempts to lock S1, S1 should get blocked, and at that stage, so that's one thing which the OS will do, and that at that stage also this particular task is going to proceed. It is now going to attempt to lock S1, and it will go ahead. So basically, we'll see how the effect plays out, but basically task 2 is going to race ahead. Okay, at this point, we will see the effect that S1 gets blocked, and this way we kind of finish. So let's see how it sort of works out. So one particular version of this protocol is called OCPP. And what happens in this case is that each process, each task, has a default priority assigned to it, and which is just according to our normal procedure, according to its rates. But each resource also has a priority assigned to it, which is called the ceiling value, and this is the maximum priority of the processes that use it. So in our example, S1 and S2, both of them will have the priority of tau1 as their priority ceiling, okay, the two shared resources. And then we introduce a concept of a process having a dynamic priority. And the dynamic priority of a process is the maximum of its own static priority and any priority it inherits because it is blocking a higher priority process. So if a process is ever in a situation that it is using a resource and that resource is being used, is needed by a higher priority process, like might happen if I'm, that basically was happening at this point out here. Okay, it needed S1, but task 1 was blocked on S1. So anytime a process is using a resource for which a higher priority process is waiting, then this process, its priority will bump up. Okay, so and it will bump up to the priority ceiling of the resource. So again, the concept is if a task is using a resource and that resource is needed by a higher priority task, then the first task, its priority will bump up to the maximum of its native priority and the priority of the resource. Okay, and the way the operating system keeps track of this thing is, remember, tasks are not communicating with each other, right? They are only indirectly communicating via the processes, by the resources. So essentially, we attach a priority ceiling or ceiling value to each resource so that we can inherit this thing. So now we have introduced a concept of dynamic priority. A second issue is the following: a process can only lock a resource if its dynamic priority is higher than the ceiling of any currently locked resources, excluding any that it has locked itself. So what it's saying is, if a process attempts to lock a resource, then it will succeed only if the current priority of the process is higher than any resource which is currently locked. Okay, and that exactly is what is happening out here. Tau1 attempts to lock S1. Now, Tau1's priority, let's say we just refer to priority as 1. So Tau1's priority is 1. There is a resource S2 which is already locked in the system, and S2's priority is also 1. So the reason the locking fails out here is because Tau1's priority is not higher than a locked resource priority. So that was the preventative action, that if there exists a resource in the system which is locked and whose priority is equal to or more than my priority, then I should not proceed, because there is a risk of deadlock happening in that case, because it's possible that whosoever has locked that other resource might need the resource that I'm going to just lock. Right? So S1 and S2, both of them, because they're shared by both, they both have a priority ceiling of the same as task 1's priority. Okay, so yeah, go ahead.
So S2's priority was 1 after it has been locked.
No, the priority ceiling. So let's go back to our definition in this case. Each resource has a static ceiling value. Okay, so this is just known at compile time. So S1 and S2 have a priority ceiling. So what would happen in the system is that you'll create these shared resources and tasks, and we'll also tell the operating system which tasks can use these resources. So the OS knows S1 can be used by task 1 and 2, and S2 can be used by task 1 and 2. And the OS also knows that priority of task 1 is 1 and priority of task 2 is 2, 1 being higher priority. So then the ceiling value associated with S1 is the max of the 2. Okay, so all of this can be done upfront, right? The moment I have all the resources and all the tasks, I know all the information. So S1 and S2's priority ceiling is a static value, it's not changing. The only thing that is changing about the resources, are they locked or not? And the key step which is happening in our system is that when tau1 appears to lock S1, it will not be allowed to do so. And the reason it is not allowed to do so is that there already exists a resource in the system which is locked, not locked by tau1, okay, but locked by someone else. That resource is S2, and S2's priority ceiling is equal to or higher than tau1's. Okay, so therefore it will not be allowed to proceed, and we are going to get this effect.
So if it is unlocked, the ceiling doesn't count.
Then doesn't count. Okay, so if S2 wasn't locked, then tau1 can race ahead safely. Okay, but because S2 was locked, then there is a certain chance that I may run into trouble, because the tau2 may need. There's a chance of a deadlock now, so we are just preemptively not going on that path. Yeah.
I may have missed this when we first started on this topic. Why does the OS allow tasks to lock resources if we're able to trade time, for instance, on the processor for whatever's the highest priority? Why can't we dynamically allocate the resources as well to those tasks?
Well, because these are shared resources. It might be like the radio. So like, for example, it could be that there are two radios in the system, S1 and S2, and what task 2 does is it takes data from radio 2 and moves it to radio 1. So it will lock radio 2, then lock radio 1, and then exchange the data. Task 1 does in the reverse direction, for example. Okay, so the resources here represent things which have to be shared. Okay, it could also be some data structure in the system which you are manipulating, some queue or something like that. But hardware resources are a very common situation. So both resources are needed by both in these different orders, and so I need to guard against that. So the OS cannot do anything about it. This is application logic at that level, and we just have to. All the OS has to do is to make sure that the system will not deadlock. Okay, so I'm not. Hopefully, I'm conveying what's happening. Right, this is beyond operating system's control. Any other question before I move on? So I'm introducing way too many concepts in one go out here, right? I mean, there is deadlock issue, and then there is this whole thing about that I don't want a task to wait unnecessarily. But unfortunately, these two issues are entangled, right? The moment we are talking about shared resource, we also have to worry about deadlocks don't happen. Classically, like if you were to do distributed systems course in computer science, there's a very well-known problem called dining philosophers problem. Okay, sort of bunch of philosophers sitting, and there is kind of you're going to whatever cutlery that you have to use, and it may be that all of them may go on one side and block. Or another example is like cars, right? I mean, they come into an intersection and someone has to yield, okay, or have to proactively prevent entering into the deadlock. So we are facing kind of the same type of issue, that if you just go ahead and grab the resource, then you may end up into a situation where like you have to wait for the other has to wait for you. And unlike the car scenario where one party can back off and break the deadlock, in computation that is much harder. So let's think about it. Can you go back in computation? So let's say we had deadlock, right? Let's say we didn't have a smart system, so tau1 had gone ahead and taken S1, and tau2 had gone ahead and taken S2, and now I have reached a situation where tau2 needs S1 and tau1 needs S2. So we entered into deadlock. Can you think of somehow you could undo this effect?
Not possible always.
Well, so there's a concept in computing also called checkpointing. I can periodically save the state of my process. And if I run into some issue, I go back. I restore the state. Okay. Now that can be done for if computation doesn't have a physical side effect. Unfortunately, you cannot undo physical effects that easily, right? I mean, if it would be pretty awkward if I have to physically move things backward also and all. That is not simply unrolling the computation, but also undoing some physical effect. If you have already started, I don't know, let's say you are injecting a patient with drugs which have two halves to it. If you've already injected one, you cannot uninject it, right? So physical effects are not always undoable, but purely computational things you could potentially undo at a lot of cost, but it's in theory doable. But better strategy is to avoid getting into those situations, okay? There should not be a deadlock. So this OCPP, then what it results in is this nice property that the high, and we'll see it in terms of an example, that with OCPP, and by the way, I think it stands for Original Ceiling Priority Protocol. Okay, as you can imagine, since it's original, so there's something else coming. But kind of the main thing is that we avoid the situation that a high priority thing will have to block multiple times. So let's look at an how OCPP plays out here. So this is back to our original example, which, just to refresh your memory, was like this, right? L4 needed both resources, L3 needed V, L2 needed nothing, L1 needed Q. So what happens now is L1 comes first, it starts executing, locks Q, okay, and now at t equal to 2, L3 arrives. L3 starts executing, and L3 will need V at this point. At t equal to 3, L3 needs V, except what will L3 see? L3 sees it's trying to lock a resource V, but there already exists a resource Q, which is locked, and Q was shared with L4 and L3, so Q's priority ceiling is 4. So there exists a resource in the system which is locked, not locked by L3, and L3's priority is not higher than that. So L3 will not lock V now. Okay, at this point, at t equal to 3, L3 attempts to lock V, but it will fail to lock V because of our protocol in place. At this point, L4, so at this point what happens is L3 can't run. L2 L2 will arrive and will not run, but instead L1 will run. And why? The reason L1 will run is the following. At this point, L1 is blocking L3, right? And therefore, L1's dynamic priority at t equal to 3 jumped up. It jumped up to that of L4, right? Oh, sorry, it jumped up to that of 3. Thanks for correcting me. So it jumped up to that of 3. So L1 will run, and then L4 arrives. And now L4 will get the CPU because the highest priority thing, but then L4 attempts to lock V. But again, the same priority ceiling protocol kicks in. L4's priority is not higher than that of the resource already locked. So L4 will block, and then L1's priority is now that of 4. So it will go ahead and run. Moment L1 relinquishes Q, at that stage, L1 runs and kind of the sequence follows. And this one has a pretty nice property, as you can see, that L4 was stopped only for 2 time units out here, okay? And in fact, you could show that the worst case it can ever block with any arrival times and all, with this thing would be at most 4, because it's possible that it was just unlucky and L1 needed to execute all 4 time units. So what this protocol results in is that the maximum amount of time process can block is equal to the maximum situation where there is a resource in the system. So if I'm looking at like the ith task, then the worst case situation that it will have to be blocked by a lower priority task is if there is a resource in the system which is used by a lower priority task and a higher priority task, because then this guy may have to wait. So what this is saying is that for across all resources, there are k resources in the system, so across all resources, we want to make sure that we are looking at the maximum where CS of k is the time needed to use that resource, so CS of k, and usage k comma I is a indicator function, it's a binary valued function, and it is 1 if the resource k is used by a task lower priority than I and higher priority than I. So essentially I is sandwiched in between. Or another way of saying is that, so let's say I was task number 3. So this is saying usage k comma I is 1 if some task lower than 3 is using it and some task higher than 3 is using it. So that potentially it will get blocked. Let's think about it. If the resource was used only by tasks higher than 3, then I don't care about it, right? If I have a task, if I'm looking at task number 3 and I have a shared resource which is used by 2 tasks which are both higher priority than me, then I don't have to worry about this. Why don't I have to worry about this? So shared resource used only by higher priority tasks. So I'm basically stating that I don't have to worry about its effect on the current task.
They finish using the resource first before it became.
They are high priority tasks. They would have anyway preempted me, right? So whether they're using a shared resource or not, who cares, right? I mean, they would have won out irrespective. So if a resource is only used by tasks higher priority than me, I don't care. If a resource is used only by tasks lower priority than me, then I will always triumph over them. So I don't have to worry about them. It's only when a resource is used by something lower than me and something higher than me that I have this possibility of the whole priority inversion and all kicking in, right? So that is what, so usage k comma I being 1 is indicating that, this is a resource which impacts me. And how much can it impact me? Well, basically, so there's a simplified thing we are saying out here that CS of k is the amount of time that resource is needed. We are basically saying whosoever uses resource k, it doesn't use it for more than CSK in one stretch. So if it is a radio, we are going to, let's say the radio has a function called read packet and write packet. Well, the maximum amount of time any task can use the resource is CSK. You can enrich this model to take into account different usages and by different ones and all, but this is a simplified model. And then because of our deadlock prevention mechanism, I can only be blocked once. That is what this guy is bringing into picture. So that's OCPP. It's accomplishing multiple goals. It is, instead of getting blocked once for every shared resource, I only will get blocked once by the maximum, whatever, most time consuming resource, and I will never deadlock. There is a subsequent work which came out called ICPP, which is called Immediate Ceiling Priority Protocol, and it works somewhat differently. So in this particular case, each process again has a static, whatever, standard priority. Each resource has again the maximum, the way we had defined the static ceiling, and a process has a dynamic priority that is the maximum of its own static priority and the ceiling values of any resources it has locked. This phrase, ceiling value of any resources has locked, is critical. What this is saying is the moment I lock the resource, I get the priority of that resource. Whereas in the original scheme, my priority, the dynamic priority will go up only when I'm actually blocking someone. Here, the moment I lock a resource, my priority goes up. Okay, and you will see the effect out here. L1 starts using, does the normal execution, locks Q. The moment it locks Q, the priority of L1 will become that of L4 because Q was shared with L4. And so now what will happen is at t equal to 2, L3 and L4, sorry, L2 and L3 arrive, but since L1 has the higher priority, L1 keeps running. Okay, and then L4 arrives, and then it has to L4 arrives, but it still has to wait because L1 is already using the CPU, but then L4 keeps running. This one looks better in this particular figure, but its worst case performance is the same. That is, it's the same formula that applies here also. So this ICPP and OCPP in their worst case performance are exactly the same, but they have different characteristics. So one advantage is that ICPP is much easier to implement because in the original scheme, I have to keep track of, like, the dynamic priority will change every time someone else does something. Whereas with ICPP, when I lock a resource, I change the priority. So there is less work to be done by the operating system. ICPP also leads to less switching of the tasks. Worst case behavior is same, but ICPP is an easier to implement scheme. So basically, it came later, and it's the one which gets used. Simple priority inheritance. If we had implemented, if we don't use these ceiling protocols, if we simply say we inherit the thing, inherit the priority, unfortunately, they don't avoid deadlock problems. Now, in this example, there is no possibility of deadlock because deadlocks only happen when you have nested resources. Okay, in this case, there was no nested resources. So that by nested, I mean I grab one resource and then I grab another resource before I release the first one. So that's not the case out here. But what you do see out here is, without the ceiling protocol, L4 is getting blocked multiple times, and that results in one can easily show that the behavior, if you were to not use the ceiling protocol, is that instead of this max out here, you will have a sigma out here. I may get blocked once for every shared resource in the system, which is not a desirable thing to have. So long story short, somewhere by early 2000s, these things were kind of understood well enough, analyzed well enough, and all that. That's at least to the first order, we know how to deal with this thing, and these are standard things in operating systems which cater to embedded real-time space. So you can also modify our analysis from last lecture for this thing. So recall previously we had response time is equal to computation of the current task plus interference from higher priority task. But now what we have seen in today's lecture is that I can also get interference from the shared resources. And so I have this additional term called B, and that we have already provided. Actually replace this thing by max with the ceiling protocol, but if you don't have the ceiling, if you have inheritance, then it will be sigma. But the main point is that my fixed point equation changes, but it effectively just has another term, and you can incorporate that into the solution. So with a modest change and keeping track of what the shared resources are and all, one can kind of deal with these issues. It does require operating system to offer the right type of APIs, because I do need to know a task does need to declare upfront what shared resources it is going to need. It can't simply start using it on the fly. It can't simply say, hey, I need the radio, I want to lock it, because by that time it's too late. So you do want the task to declare upfront, I'm going to need the radio and I'm going to need this sensor, so that the operating system can construct that static ceiling value for every resource. If the tasks don't declare it, then there is no way of knowing it. So these kind of things are not present in every operating system. Like in Linux, for example, if you need something, you can just declare a time, hey, I need a mutex, start using it. It's too late by that time. Okay, you may have deadlock happening and all as a consequence. So one has to be careful in doing it. But things like VxWorks and other systems design in for these purposes have all these kind of goodies. Let's see. Okay, so yeah, so that's taken care of. Some slides I had them out of order, so you can ignore them. Okay, so in the remaining 10 minutes, I want to cover another sort of trickiness which comes in, which is the following: that thus far we again were thinking of our tasks as independent or now using a shared resource. But there's another type of interaction that happens among tasks, and which is that they send data to each other. So like, for example, we may have a situation, task 1 runs, it produces some data items which are sent to task 2 and 3. Task 2 cannot run until it gets the data item from task 1, and then so and so forth. So this is kind of a different kind of thing. A sensor sample arrives, an initial task processes it, it generates some summary of that sensor data, let's say, which is pushed to another task, and so on and so forth. So in this situation, I have a data dependency also. Task 2 cannot run until task 1 runs. Task 4 cannot run until task 2 is finished, and so on and so forth. And then our deadlines might look like, from the point the initial input arrives, maybe T6 should finish by a certain time. Or we may even have individual deadlines. What can you say about the rate? So let's say I tell you T1 has a rate that it runs once every second. What about the rate of T2?
Slower. Should be slower.
Why would it be slower? Anyone who says slow, so why do you think it's slow? So let's say T1 runs, so like I said, T1 runs once every second. How often do you think T2 will run?
If it is using the same data again.
It's using the output of T1.
It can run multiple times.
When you have the output of T1,
Hmm?
you run T2 right away.
Hmm?
So watch the second.
Say it again?
I think it's the same.
Yeah, it's the same, right? I mean, T1 produces every time T1 runs, it produces a data item, T2 uses it, right? So it will run the same amount of time, right? Same number of time, right? So T1 takes a data item, it produces a result on this edge, a result on this edge. T2 is waiting for the data, so T2 will run. Okay. Now you could say a more refined answer. Potentially, you can say, it will really depend upon how many samples produced by T1 are consumed by T2 in one go, right? So it's possible that T1 produces a sample, but T2 needs 4 of them to run. Okay, so there could be some rational ratio. But in the simplest possible scenario, T1 runs, every time T1 runs, T2 has to run. Every time T2 runs, T4. So all of these things will have the same rate. Okay, they will run, every time I get a data item, I kind of go through this graph once. Okay, unless I tell you some additional information. Right? So the rate is the same. It's neither slower nor faster. It's exactly the same. If it were to be the case that every time T2 runs, it can consume multiple samples, then I may have a more complicated situation, some sort of a rational number relationship. Okay, so the situation that you may face might look something like the following. So wherever I say EI, because I copied pictures, this is really the execution time or computation time. So what this is saying is I have 6 tasks, and when they run, their execution times are given 3, 2, 6, 2, 4, 6. 3, 2, 6, and 3, 5, 6. And the deadlines are given. So at t equal to 0, the data arrives, T1 will execute, and I have deadline of 6 on it. And on task 2, I have a deadline of 7, and so on, and so forth. So for task 6, I have a deadline of 28. So what I have is a deadline for each one of the intermediate tasks also. It could be because, for example, the output of T2 and output of T4 also have some additional effects as well. So we want to schedule something like this. Now here we have a problem because thus far in our scheduling approaches, we never really worried about these dependencies among the tasks at all of this nature, right? The data dependency. So somehow we need to sort of deal with that as well. Now it turns out these kind of problems are incredibly hard. So there's no like results of the nature that we had previously. Now you have to kind of begin to essentially get into the world of heuristics, approach these things, or some other way of doing it. So let's say we are faced with this problem. How can you think of some intuitive ways you can approach this problem? How would you go around? If I were to literally just give you this thing, okay, and let's forget periodicity. Let's say t equal to 0, a data item arrives, and I have to achieve this goal. How would you go around doing it?
If it is like a structure, execute the topmost level.
You mean execute T1?
Uh.
Okay, so t equal to 0, I start executing T1.
Okay.
T1 will finish at time 3. So it has met its deadline. Okay.
Then T2, T3.
Okay, so now once T1 is finished, I have 2 candidates to run, T2 and T3. Right? So which one would you run?
If we can keep
T2. The deadline is.
Okay, so one intuition you would say is T2's deadline is 7, T3's deadline is 20. Obviously, there's a lot of laxity out here, so I will run T2, right? But that's not necessarily always the right choice because you are only doing a look ahead into this one. Maybe let's say the deadlines were a lot closer, and then there were some subsequent deadlines which were a lot tighter, right? So this is a problem where you basically will have to, essentially you have to search for all the possibilities. But your intuition, the first order is right, that one way I could do it, I can essentially start from the beginning, and every time a task becomes eligible to run, I include in a set, and then every time I have to figure out which task to run, I do some heuristic. Your heuristic was that I will do the one whose deadline is earlier.
Can we predict the max time, like some sort of a max dependency to the last level and store it at the node?
Okay, indeed. Yeah, so look, firstly again, to solve this problem exactly, you have to search through everything in the worst case. Can you think of some other heuristic? So proposal 1 was we start from the top. Do you think you can start from the bottom? And if so, how might you do it?
Start the deadline for T6 and work backwards.
Okay, so our deadline was same, so I execute T6. Okay, at the very end. I had another candidate to run, which was T5, but T5's deadline was at 27, right? So I could have, so I did T6, and I kind of go backward and then kind of start putting things in, and then at the end I can just squish everything to the beginning. So you can formulate a heuristic from back also. Okay, let's say I give you, use MATLAB. How would you do it? No. Is there some standard way you can formulate this problem? So how many of you have heard of linear programs? Linear programming. Anyone done linear programming? So Corey, what is it?
It's just you have an optimization function that's linear, and then you have constraints that are also linear.
Terrific. So essentially any problem where I have a bunch of variables and I can express an optimization function which is linear as a cost function which is linear, and I can express constraints on those variables of the form which are also linear, in the sense that linear, like let's say I have two variables x and y, so I can say optimized for 2x plus 3y given that, I don't know, x plus y is less than 5 and x minus y is greater than 4. I'm just making them up. Now that's an example of a linear programming problem, except in this case x and y are real numbers. There is a much harder problem called integer linear programming, where x and y are limited to being integers. Actually, it's much harder because when x and y are real numbers, then it can be done in polynomial time, although you don't necessarily use those algorithms, but it's an efficient algorithm. Okay, so real numbers, linear programming, done routinely with millions of variables, great solutions. The problem where x and y are integers is super hard. Okay, although again, very good algorithms have emerged, so we can do fairly large problems, but it's a problem which is not polynomial type. The claim I'm making is that these kind of problems you can write as an integer linear program problem. Okay, now I'll just give you the intuition on how one might go around doing it, but one way of thinking about it is that I could create, let's see how I'm doing at time. Okay, I'm already exceeding, so I'll pick this up next time. But the idea is that I can express, remember, all my time variables here are integer. I will create what are called as indicator variables. I will create variables where I would say, let's assume that T1 can start in a whole bunch of time slots. It can start at t equal to 1, t equal to 2, t equal to 3. So I consider all those possibilities and then put constraints like T1 start time and T2 start time. Can you think of a linear constraint between them? So let's say I have variables corresponding to start time of the tasks. Can you think of a linear constraint between start time of T2 and start time of T1?
T2 should be greater than deadline or completion of T1.
Start time of T2 has to be after start time of T1 plus execution time of T1, right? So for every edge, I can write a constraint. And there will be other constraints, and there will be constraints because of deadlines, right? I have to make sure end time of T2 is less than 7, right? Which is another way of saying start time of T2 plus execution time of T2 is less than 7, and so on and so forth. So I can write a bunch of constraints like this, feed it into your favorite ILP solver, integer linear programming solver. They're available for MATLAB for sure, but in Python there are excellent ones. You just feed it in, and voila, your solution comes out. And for toy problems like these, you will get the exact solution in like milliseconds. But even much larger problems you can kind of solve it this way. So scheduling can also be done by just mapping it to this integer linear program and then doing it. It's probably not something your OS is going to do, but if you are doing if a compiler is doing it, it's a great option for it. Okay, so heuristics or using these ILP solvers. So I'm going to stop out here, and we'll. So I'm going to be in my office for another hour or so. So feel free to come by.